Let's talk about cooking. I'm going to bring up a particular cooking problem, and that's cooking hot dogs. And I'm going to start with a quick demonstration here. Okay. Turns out, hot dog, this is a Value Red Frank from Safeway. These are pretty consistently developed industrial products. I mean, they're consistent length, consistent cross-section area, and also consistent resistance. If you pull these Franks out of the package, measure the resistance, it's pretty consistent. They're about a 200 ohm resistance. It's got a lot of salty water in there. If you look at the ingredients, there's a lot of water. It's dripping a little bit even, and they're pretty salty. If I take this and I put it here, I can take it and I can connect it to the 120 volts electric outlet. And so what I'm going to do is this. I'm going to plug in this power cord, and I'm just going to hook this into the two sides of the hot dog, right like this. Stick a wire in like this. And then what happens is, when I turn it on, there. And that's what happens. And what happens is, it warms up. Because it's just a resistor in a circuit with a power supply, right? And then it gets kind of like dried out, and then it starts to catch on fire. That's not so good. But until then, it kind of warms up, and it's perceptibly warmer than when I started, which is kind of cool. Don't try this. Don't try this at home. I'll mention one thing, though. The power cord that I used for this has got one of these ground fault interrupters on it. And really, you shouldn't play around with stuff like this. I'm being a bit cavalier. But I've taken some precautions. And how this particular element, using this thing in the circuit, protects me is something we'll talk about when we get to AC circuits, and we'll talk about safety. And that was the smokiness, not necessarily so good. But I'm going to do the same thing. The problem was the electrodes are too small, and it dries out the electrodes, and then it catches on fire. But I got this device right here. And this device, it's got this little tub here, and it's got electrodes in it. And I take this, and I connect it from one electrode to another electrode. And this electrode is hooked to this. This electrode is hooked to this. And I take this thing, and I plug it in. And that's connected to this. And if I plug this in, I've done exactly the same thing electrically. The hot dog is just hooked across 120 volts. And here's what happens. It gets warm. And because I'm passing an electric current through it. And see, I'm just like electrically heating it. And we'll let this go on for a couple of minutes, and then the aroma of Value Red Franks will fill the room. We'll kind of leave this here. I got that at a garage sale. And I got this from a woman, and she said, oh, yeah, and like 20, 30 years ago, I'd have all these kids over at my house, and everyone's hanging out, and I had to feed all the kids in a hurry, and this was before we had a microwave oven, and so I would use that every day. I was cooking up hot dogs like crazy for these kids. It's like 120 volts. The resistance of the Franks are about 200 ohms. We can work out how much power that produces. Power is equal to delta V squared divided by R. What is the potential difference? What's the voltage? 120 volts squared divided by the resistance, 200 ohms. I get a power of 72 watts. Now, that's not so much power, but it's only heating up, a pretty small food item. And so at this point, it's actually steamy. Oh, yeah. And if I take this and open it up, steamy. And this is done. It's ready. And so this was like this 70s answer to the microwave oven. Seriously. You can get these things and heat them up that way. If anybody wants this, I'm going to leave it here. And you can snag it at the end of class. Just going to leave that there for you. Oh, yeah. But really, it's kind of a direct electrical heating technique. It's really quite remarkable. Now, here's another problem that we can solve this way. And ultimately, it's the same problem. But there's a little bit more detail here. If you go to motorcycle websites, there's instructions as to how you can make clothing to help keep yourself warm on winter rides. And the great thing is, if you're riding a motorcycle, you have a battery that starts it up and runs the lights and things like that. And it can provide a fair amount of current. And so you can basically plug in to your battery. And you can plug a length of wire, current goes to the wire warms up, and you can use this to heat you up. And this is a recipe that I found on a website This is the length, and this is the diameter of the wire which you have to have. Let's calculate how much heat, how much warming are you going to get from this. And here's how we solve this. Step one, let's draw a circuit diagram. Circuit diagram looks like this. It's a power supply connected to a resistor. And what's the potential difference? What's the voltage of the power supply? 12 volts. Excellent. And then I got a length of wire. The length of the wire is the resistor in the circuit. And when I have a resistor and it's connected to a potential difference, current flows. And the current, of course, is just equal to delta V divided by R. And so that's all good. Ultimately, what we're interested in here, though, is the power, right? The question asks for how much power will this vest provide to warm the wearer. And the power is equal to delta V squared divided by R. Why do I choose this version of the equation? Because I know, what do I know in this equation? The voltage. I know it's 12 volts. And so this is, I don't know the current, but I do know the voltage, and so this is going to work great for me, this one right here. In order to be able to compute the power, what do I have to know? Resistance. Okay, and so here's how you're being guided. You say, okay, it's a vest, it's power, I'm passing a current. This is an expression that gives me the power based on the potential difference, the resistance. I know the potential difference. I know the voltage. It's 12 volts. I just have to figure out the resistance. But the resistance, it's a piece of copper wire, right? And the resistance of a piece of wire is equal to the resistivity times the length divided by the area. Do I know the length? Yep, 10 meters, right? That's 10 meters. Do I know the area? Well, I know I'm told the diameter. So the area is going to be pi times r squared, and r is 0.125 times 10 to the minus 3 meters squared. How about the resistivity? Do I know the resistivity of copper? Yeah, because we can look it up. There's a table in the book which has that. Resistivity of copper, 1.7 times 10 to the minus 8. And that's ohms times meters. Excellent. And so I can calculate the resistance. And if I do that, I get a resistance of 3.5 ohms. 3.5 ohms. And then I plug it into my power expression. I take that number, and I put it in here. And then I calculate a power, delta V. Delta V in this case is 12 volts squared divided by the resistance, 3.5 ohms. And so I get a power of 41 watts. How much does your body make typically? If you're sitting on a motorcycle and you're not working particularly hard. Do you remember from the first semester, like typically how much energy is your body making? 100 watts or so? So this will help a little bit. This will help, and actually it will help take the edge off. And it might be just enough to help keep you warmer.